Welcome to Ultimate Sleep Doctor. Tonight, we'll explore a fascinating realm of possibility. The universe, as we perceive it, might be far more intricate than our eyes can see. Physicists have proposed a theory, string theory, suggesting that the smallest components of reality aren't points, but incredibly tiny vibrating strings. These strings, dancing with energy, create all that we experience. It's a beautiful, almost musical idea, hinting at a deeper harmony within existence. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift like clouds across the sky. Let's begin. The seeds of what would become string theory weren't planted overnight, of course. They sprouted slowly, nurtured by brilliant minds wrestling with the fundamental nature of the universe for almost a century. It begins, surprisingly, with a story of frustration and a revolutionary idea about gravity, a story woven into the fabric of Einstein's own thinking. Einstein, you see, was a man haunted by a nagging problem. He'd achieved a monumental victory in 1915 with his theory of general relativity. This theory described gravity not as a force, like Newton's, but as a curvature of space-time, the very stuff of space and time, caused by the presence of mass and energy. It was a breathtaking achievement, predicting phenomena like the bending of light around massive objects and the existence of gravitational waves. Yet general relativity didn't play nicely with another remarkably successful theory: Albert Einstein's own theory of special relativity. Special relativity, formulated in 1905, described the universe as a smooth, unchanging space, governed by the constant speed of light. When Einstein tried to combine these two theories into a single, unified description of gravity and space-time, he ran into a significant roadblock. The equations simply didn't work. They produced nonsensical results, predicting runaway gravitational effects that were far too strong, especially in the early universe. It was as if space-time itself was screaming in protest. Einstein spent the next several years wrestling with this inconsistency, a period often described as his crisis of 1916-1917. He realized he needed to fundamentally rethink what he was assuming about space-time. He began to explore the possibility that space-time wasn't the rigid, unchanging backdrop he'd previously envisioned. Instead, he considered that space-time itself might be dynamic, potentially expanding or contracting, just like a balloon being inflated or deflated. This radical idea led him to develop his theory of general relativity in its final accepted form, one that incorporated this dynamic space-time. It was a brilliant, albeit initially unsettling, compromise. Einstein essentially said, "Okay, space-time is doing something. It's reacting to the presence of matter and energy." He introduced the concept of the metric tensor, a mathematical tool that described the precise way space-time was curved at any given point. The metric tensor allowed him to accurately predict gravitational phenomena, cementing his place in scientific history. However, the problem of reconciling general relativity with special relativity didn't vanish completely. Physicists continued to search for a deeper, more elegant solution. Then, in the early 1960s, a group of theorists, most notably Gerald Brands and Morris Dick, took a completely different approach. They were investigating a long-standing, albeit largely dismissed, idea: the possibility that the universe wasn't simply expanding in space, but actually expanding in time. This concept, known as cosmological time-dependent symmetry, proposed that the fundamental laws of physics themselves might change over time. The prevailing view at the time was that the laws of physics were constant and unchanging, a cornerstone of scientific thinking. Brands and Dick argued that if spacetime was dynamically changing in time, then the constants of nature, things like the gravitational constant or the speed of light, might also vary over time. Their research was driven by a specific mathematical model they developed, the Brands-Dick theory. This theory wasn't intended to be a complete theory of gravity, but rather a modified theory that incorporated the idea of a dynamic spacetime. The Brands-Dick theory introduced a new field, called the Brands-Dick field, which was linked to the dynamic spacetime. This field had a mass, and its properties influenced the curvature of spacetime, and consequently, the strength of gravity. The theory predicted that the gravitational constant, g, might not be truly constant throughout the universe's history. It could, in fact, be slightly different in the distant past, perhaps during the very early universe when the conditions were radically different. The Brands-Dick theory was, and remains, a fascinating case study. It wasn't a revolutionary breakthrough in its own right. It failed to fully predict many observations, particularly those related to the cosmic microwave background radiation, the afterglow of the Big Bang. However, it served as a crucial stepping stone. It demonstrated the viability of a dynamic, time-dependent spacetime, a concept that would later become central to the development of string theory. The theory provided a framework, a mathematical language, that could be used to explore the possibility that the fundamental building blocks of the universe were not point-like particles, as was assumed in the standard model of particle physics, but rather tiny, vibrating strings. The Brands-Dick theory's shortcomings weren't a failure. Instead, they highlighted the need for a more comprehensive framework. It forced physicists to reconsider their assumptions about spacetime and gravity, and it planted the seeds for a radical new idea: that the fundamental constituents of reality might be unimaginably small and intensely energetic, and that their vibrations could explain not only gravity, but also all the other forces in the universe. The story of Einstein, general relativity, and the Brands-Dick theory wasn't an ending, but a crucial prelude to a truly astonishing chapter in the quest to understand the universe. The universe, as we understand it, isn't made of tiny billiard balls, those little hard spheres that physicists once imagined as the most fundamental building blocks of reality. The Standard Model, our best current description of particle physics, uses these fundamental particles, quarks, leptons, and force carriers, but it's filled with a surprising number of unanswered questions. It's a very successful theory, certainly, but it feels incomplete. Then came the idea of strings. The core concept of string theory begins with a startling proposition: that what we perceive as particles, the very essence of matter and energy, aren't actually particles at all. Instead, they're incredibly tiny, vibrating strings. These strings are so incredibly small, far smaller than even an atom, that they appear to us as point-like particles. It's like looking at a vast ocean and mistakenly believing every wave is a single, isolated entity when in reality, they're all ripples of the same water. These strings aren't just static lines, they're dynamic, constantly moving and vibrating. And it's the patterns of these vibrations that determine what a string appears to be. Think of a guitar string. When you pluck it, it vibrates at a certain frequency, producing a specific note. That note is determined by the length, tension, and mass of the string. Similarly, a string in string theory vibrates at specific frequencies. Each different vibration corresponds to a different particle. One vibration might produce a photon, the particle of light. Another vibration could create an electron, a fundamental building block of matter. Yet another vibration could yield a graviton, a hypothetical particle that would mediate the force of gravity. It's not that the string becomes a photon or an electron when it vibrates. Rather, the vibration itself is what we perceive as that particle. It's a beautiful and profound connection. The key to understanding this lies in the mathematics, specifically the concept of modes. A mode describes a particular standing wave pattern that a vibrating string can produce. It's a mathematical description of how the string is oscillating. Just like a guitar string can have numerous different modes of vibration, each corresponding to a different frequency, and therefore, a different note, a string in string theory can exist in countless vibrational modes. Each mode is characterized by its frequency, how many times the string vibrates per second, and its shape. These shapes aren't just simple circles. They can be incredibly complex, involving intricate patterns of oscillation. The higher the frequency, the more energetic the vibration. And the more complex the shape, the more different particles, or more accurately, modes, can be created. Now, let's consider the implications. If different particles are simply different vibrational modes of the same fundamental string, then we have a single, elegant explanation for the entire spectrum of particles we observe. It avoids the need for entirely new particles to be added to the standard model to account for different forces and interactions. The beauty of this approach is its inherent simplicity. It's a single, unified theory that could potentially explain everything from the behavior of subatomic particles to the expansion of the universe. But of course, string theory is incredibly complex. The mathematics involved is extraordinarily challenging, and it's proving difficult to make concrete, testable predictions. The frequencies themselves aren't just arbitrary numbers. They're intimately related to the fundamental constants of the universe, things like the speed of light and the gravitational constant. These constants aren't just random numbers. They are woven into the very fabric of the string's vibration. The precise value of a frequency depends on the properties of the string and the energy scale at which it's vibrating. One particularly interesting aspect of this concept is the idea of extra dimensions. String theory suggests that the universe isn't just the three spatial dimensions, length, width, and height, that we experience. It proposes the existence of additional, curled-up dimensions, so small that we can't directly perceive them. These extra dimensions influence the vibrational modes of the strings and therefore determine the properties of the particles we observe. Think about a garden hose. From a distance, it appears to be a one-dimensional object, a line. But if you get closer, you see that it has a circumference, a second dimension. Similarly, the extra dimensions in string theory are curled up at incredibly small scales, influencing the way the strings vibrate and, consequently, the properties of the particles. The mathematical tools used to describe these vibrational modes are often based on something called supersymmetry. Supersymmetry proposes that every known particle has a corresponding superpartner, a particle with different spin and other properties. These superpartners haven't been detected yet, but their existence would provide strong support for string theory. The exploration of string theory is still ongoing, a vast and intricate mathematical landscape filled with possibilities. It's a challenging field, but it offers a tantalizing glimpse into the fundamental nature of reality, a reality where particles aren't solid spheres, but instead incredibly tiny, vibrating strings creating the universe, note by note. The fundamental idea underpinning string theory is a rather startling one. The universe, as we perceive it, isn't quite complete. It's not simply a four-dimensional space, length, width, and height, combined with time. Instead, string theory proposes that the most basic building blocks of reality aren't point-like particles, but incredibly tiny, vibrating strings. And these strings require more than just four dimensions to exist stably. The mathematics simply won't work otherwise. The universe, according to string theory, has a much greater number of dimensions, typically 10 or 11, depending on the specific version of the theory. These extra dimensions aren't easily grasped. We live in a world where we experience three spatial dimensions directly. It's natural for us to think of dimensions as having a size we can readily perceive. However, these extra dimensions aren't like the ones we're familiar with. They aren't, for example, a large hallway we could walk through. Instead, they're thought to be curled up, incredibly small, and hidden from our everyday observation. They're so tiny, they're essentially undetectable with current technology. Now, how do we mathematically describe these curled-up dimensions? That's where the concept of Calabi-Yau manifolds comes in. A Calabi-Yau manifold is a specific type of mathematical shape, a complex, multi-dimensional space that arises naturally when string theorists try to compactify these extra dimensions. Compactification is the process of taking these extra dimensions and rolling them up into incredibly small spaces. It's like taking a garden hose and squeezing it. The length remains the same, but the diameter is reduced. These manifolds aren't just random shapes. They possess a remarkable symmetry that is crucial to the mathematical consistency of string theory. They're characterized by a property called complex structure, meaning they're built using complex numbers, which adds to their inherent mathematical elegance. Each different Calabi-Yau manifold corresponds to a slightly different set of properties for the particles we observe in our three-dimensional world. It's as if the shape of these curled-up dimensions dictates the way the strings vibrate, and consequently, the types of particles they produce. There isn't just one Calabi-Yau manifold. There's a whole family of them, each with varying complexities. Some are relatively simple, like a torus, a donut shape, while others are incredibly intricate, possessing hundreds or even thousands of faces, mathematical structures that describe the detailed geometry of the compactified space. The choice of which Calabi-Yau manifold to use has profound implications for the physical laws of our universe. Let's consider the torus as an example. When a string is compactified on a torus, it behaves differently than if it were compactified on, say, a more complex shape. This difference in behavior manifests as variations in the masses and charges of the resulting particles. For instance, the top quark, a heavy particle, might have a different mass if the extra dimension is shaped like a torus. The shapes of these manifolds are explored using tools from topology, geometry, and complex analysis, branches of mathematics that deal with the properties of shapes and spaces. Physicists and mathematicians collaborate intensely, trying to understand the relationships between the geometry of these Calabi-Yau manifolds and the properties of the particles they influence. It's a highly sophisticated and challenging area of research. Furthermore, the concept of compactification introduces the idea of branes. These are higher dimensional objects, membranes, if you will, where the strings can live. Our three-dimensional world might be a membrane floating in a larger, higher dimensional space. The interactions between strings on different branes could explain various phenomena in the universe, such as the forces between particles. The search for the correct Calabi-Yau manifold, or perhaps a collection of manifolds, is a central goal in string theory research. Scientists are constantly developing new mathematical techniques to explore these hidden dimensions and to understand how they might be related to the observable universe. It's a journey into the deepest layers of mathematical and physical reality. The beauty of string theory lies in its ability to potentially unify all the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, into a single, elegant framework. If the extra dimensions are real, they could provide the missing link in our understanding of the cosmos. The exploration of these hidden geometries isn't just about finding a mathematical solution. It's about understanding the very fabric of existence. Ultimately, the quest to understand the Calabi-Yau manifolds and their role in string theory represents one of the most ambitious and intriguing endeavors in modern science, pushing the boundaries of our knowledge and challenging our fundamental perceptions of space, time, and reality itself. The elegant equations of string theory, describing the universe as woven from vibrating strings, presented a beautiful picture, but it also faced a significant challenge, a problem with mass. The fundamental strings themselves, according to the theory, possessed a particular mass, a tiny but measurable value. If string theory were truly correct, and if every particle in our universe, the quarks, the leptons, the force carriers like photons and gluons, originated from these vibrating strings, then the universe would be brimming with particles, each possessing this same inherent mass. This would create a chaotic, unstable scenario, a kind of particle soup where interactions would be infinitely complex and incredibly strong. It wasn't a situation conducive to the relatively calm and predictable universe we observe. Something had to be done to address this immediate instability. The solution, proposed in the late 1980s, came in the form of a radical idea: supersymmetry, or SUSY for short. Supersymmetry postulates a fundamental symmetry within the universe, a mirror symmetry between bosons and fermions. Bosons are the force-carrying particles, the photons, the W and Z bosons that mediate the weak force, and the gluons that hold the atomic nucleus together. Fermions, on the other hand, are the fundamental building blocks of matter, the quarks and leptons. SUSY suggests that for every known fermion, there exists a corresponding boson partner, a superpartner. These superpartners, often referred to as sparticles, weren't just theoretical additions. They were considered absolutely necessary for the consistency and stability of string theory. The existence of these particles was intrinsically linked to the mathematical framework of the theory itself. Researchers began to suspect that the original, massless strings within string theory weren't truly fundamental. They were, in fact, the lowest energy states of their superpartner particles. Just as a guitar string can vibrate at multiple frequencies, each corresponding to a different energy level, these superpartner strings could exist in higher energy states that would give them mass. The most immediately anticipated sparticle was the gravitino, the hypothetical partner of the graviton, the force carrier of gravity. The gravitino was expected to have a mass that was incredibly small, perhaps on the order of the Planck mass, a unit of mass that combines three fundamental constants of nature: the gravitational constant, the speed of light, and the reduced Planck constant. This tiny mass would help to tame the runaway mass problem. Alongside the gravitine were the squarks, superpartners of the quarks, and sleptolians, superpartners of the leptons. Alongside the gluinos and charginos, each of these particles would come with its own specific mass, determined by the mathematical structure of the theory. But the role of supersymmetry extended beyond simply providing a mechanism for mass generation. It also offered a potential solution to a more profound issue: the hierarchy problem. This problem concerns the vast difference in scale between the weak force's fundamental strength and the energy scale at which gravity becomes significant. Without SUSY, the calculations predicted that the Higgs boson, the particle responsible for giving other particles their mass, would have to be incredibly heavy, vastly heavier than what we observe. SUSY elegantly solved this by introducing the superpartners into the Higgs mechanism. The existence of these heavier superpartners effectively diluted the Higgs boson's mass, bringing it down to its observed value. It was a beautifully intertwined solution. The precise masses of the superpartners remained unknown, and this uncertainty has been a central challenge for string theorists. The models predict a wide range of possible masses, and experimental searches have yet to definitively detect any of these particles. However, experiments at the Large Hadron Collider, LHC, at CERN are actively searching for evidence of sparticles. The hope is to find evidence for the lightest supersymmetric particles, which would provide the strongest indication that SUSY is indeed a real phenomenon. Furthermore, SUSY profoundly impacts our understanding of compactification. the process by which the extra dimensions predicted by string theory are curled up into tiny, unobservable spaces. The stability of these compact spaces relies heavily on the existence of superpartners. The interactions between the superpartners contribute to the overall geometry of the compactified space, and their masses play a crucial role in determining the size and shape of these hidden dimensions. The implications of SUSY extend far beyond just particle physics. It fundamentally alters our understanding of the cosmos itself. The existence of dark matter, the mysterious substance that makes up about 85% of the universe's mass, could be explained through the contribution of stable, weakly interacting SUSY particles, neutralinos, for example. These particles, if they exist, could be the dark matter candidates that scientists have been searching for. It's a remarkably elegant and interconnected picture, where the fate of the universe could be inextricably linked to the properties of these unseen superpartner particles. Despite the ongoing experimental challenges, the pursuit of supersymmetry remains a cornerstone of string theory research. It's a testament to the power of theoretical ideas, to the belief that even the most complex and seemingly intractable problems can be resolved with a deeper understanding of the fundamental laws of nature. The search for sparticles is not just a search for new particles. It's a quest to unravel the deepest mysteries of the universe and to finally confirm the validity of string theory, a theory that elegantly weaves together gravity, quantum mechanics, and the very fabric of space-time. The work of physicists like Edward Witten in the mid-1990s revealed a rather startling puzzle concerning string theory. The initial formulations, based on vibrating strings, led to 5 distinct but mathematically related versions of string theory. Each of these type I, type IIA, type IIB, and heterotic SO 32 and E8XC8 possessed unique properties and seemed to describe different universes. It was as if 5 different, exquisitely crafted blueprints had been drawn for the very fabric of reality, each detailing slightly different possibilities. The existence of these variations wasn't a sign of failure, but rather a clue, a hint that something fundamentally deeper was at play. The common thread weaving through these diverse formulations wasn't just the idea of vibrating strings, but a profoundly complex and elegant mathematical structure. Physicists realized that these 5 theories were actually different facets of a single, underlying entity. This entity was dubbed M-theory. The M stood for membrane, or perhaps even mystery, reflecting the profound nature of the concept. It wasn't simply a new version of string theory, but a radical reimagining of the fundamental building blocks of our universe. At the heart of M-theory is the concept of extended objects, not just strings, but also higher dimensional objects known as branes. These branes are like membranes, but they can exist in any number of dimensions. They aren't just static backgrounds. They actively participate in the dynamics of the theory. Some branes are one-dimensional, like the strings we previously discussed, but others are two-dimensional, three-dimensional, or even higher. The precise number of dimensions a brane occupies is itself a fundamental parameter within the theory. The mathematics underlying M-theory relies heavily on a concept called supergravity. Supergravity incorporates the ideas of supersymmetry, the previously explored relationship between bosons and fermions, but on a grander scale. It treats gravity itself as a force mediated by a particle called the graviton, which, like other particles, emerges from the vibrations of higher dimensional branes. The equations governing these vibrations, when combined with the principles of supersymmetry, create an incredibly intricate and powerful framework for describing the universe. Crucially, M-theory suggests that our universe, the three spatial dimensions and one time dimension we experience, might be a brane embedded in a space with far more dimensions. These extra dimensions aren't simply mathematical conveniences. They are active participants in the physics of our universe. They could influence gravity, determine the masses of particles, and even explain the seemingly fine-tuned constants of nature. The mathematics of M-theory is deeply intertwined with the concept of compactification. Recall how we previously discussed compactifying extra dimensions. In M-theory, compactification isn't just a method of simplifying calculations. It's a fundamental process. The specific shapes and sizes of these compactified dimensions, often described as Calabi-Yau manifolds, complex geometric shapes, determine the properties of the particles and forces we observe in our three-dimensional universe. Different shapes yield different universes, each with unique physical laws. Furthermore, M-theory predicts the existence of a vast landscape of possible universes. Because there are countless ways to compactify and shape these extra dimensions, there are an almost unimaginable number of different solutions to the equations of M-theory. Each solution represents a different universe with its own set of physical constants, particle types, and even fundamental laws. It's like a cosmic garden, brimming with an infinite variety of floral arrangements, each representing a distinct possibility for our universe. The mathematics of M-theory provides tools to navigate this landscape. Techniques like string field theory allow physicists to treat the entire collection of strings and branes as a field, much like an electromagnetic field. This allows for calculations that can, in principle, predict the properties of our universe based on the particular configuration of branes and the shapes of their compactified dimensions. While a complete and fully tested version of M-theory remains elusive, the progress made in understanding its underlying mathematical structure is revolutionary. It suggests that our universe is not just a single, isolated entity, but one member of a vast, potentially infinite multiverse. The pursuit of M-theory is a journey into the deepest layers of reality, a quest to understand the fundamental rules governing everything that exists, from the smallest particle to the largest cosmic structures. It's a profoundly humbling and awe-inspiring endeavor, one that reminds us of the immense complexity and beauty hidden within the fabric of existence. The mathematical foundations of string theory, as we've been exploring, rely on a remarkable and surprisingly simple ingredient: the tension parameter, often represented by the Greek letter G. It's not a grand, dramatic force like gravity, nor is it a readily observable particle. Instead, G acts as a fundamental calibrator, a crucial key that unlocks the relationships between seemingly disparate physical constants we observe in our universe. Its existence initially arose as a need to connect the vibrational modes of strings, these tiny, one-dimensional entities, to the properties of the forces governing the cosmos. Consider a vibrating string. Just as a guitar string produces different musical notes depending on how it's plucked and the tension applied, a fundamental string in string theory vibrates at specific frequencies. These frequencies aren't just random, they are directly linked to the energy levels of the string. Each vibrational mode, each allowed frequency, corresponds to a different massless particle, a photon, a graviton, a W boson, and so on. The higher the frequency of the vibration, the greater the energy associated with it. The problem was, the mathematics describing these vibrations, particularly when incorporating the effects of gravity, didn't immediately yield a consistent and believable set of constants. The calculations were producing values for things like the strength of the electromagnetic force, the gravitational constant, and even the charge of an electron that were wildly inconsistent with what we actually measure in the universe. It was like a beautiful musical score with notes that were either too loud or too quiet, creating a chaotic and unharmonious sound. That's where G stepped in. Physicists realized they needed a parameter, a number, that could translate these string vibrations into the observable forces. The string theory community began to explore the possibility that G wasn't just a convenient placeholder, but rather a truly fundamental quantity. The specific value of G introduced into the equations directly influenced the energy levels of the string vibrations, and therefore, the strength of the forces that emerged from those vibrations. Initially, the value of G was taken as an arbitrary choice, a starting point. However, as string theorists continued to refine their models and try to match the observed properties of the universe, they discovered a profound connection. The particular value of G they chose, and it's a value that's remarkably close to the currently accepted gravitational constant, dictated the scale of the universe. A larger G would lead to a universe where particles were heavier and forces were significantly stronger, potentially preventing the formation of stable atoms and ultimately, life as we know it. A smaller G would result in a vastly different cosmos, perhaps one where the expansion of the universe would have been much slower, and the fundamental particles would be significantly lighter. It's crucial to understand that G isn't just related to gravity in the traditional sense. While gravity is fundamentally linked to the vibrations of strings, the parameter G itself isn't simply a measure of gravitational force. Instead, it's intimately connected to the energy scale of the universe. The vibrational modes of the string, when expressed in terms of energy, directly correspond to the fundamental forces. This connection is elegantly expressed through the relationship energy equals h stroke omega, where h stroke h bar is the reduced Planck constant and omega is the angular frequency of the string vibration. This equation tells us that the energy of a particular vibrational mode is proportional to its frequency, and this frequency, in turn, determines the strength of the force associated with that mode. The beauty of this approach is that it offers a potential explanation for why the fundamental constants have the values they do. Instead of postulating that these constants were simply set at the beginning of the universe, string theory suggests they arose naturally from the properties of vibrating strings. The value of G, which is ultimately determined by the geometry of the extra dimensions that compactify within the string theory framework, effectively determines the energy scale of the universe, and therefore the values of all the other forces. Furthermore, the implications extend beyond just the familiar forces like electromagnetism and gravity. The specific vibrational modes associated with the string, the allowed frequencies, determine the types of particles that can exist within the theory. Different values of G would lead to different particle spectra, which would, in turn, influence the overall dynamics of the universe. This introduces a level of fine-tuning that, while mathematically consistent within the framework of string theory, is still a subject of intense research and debate. Why does G happen to have the value it does? Is it a fundamental property of the universe, or is it simply a consequence of the specific geometry of the extra dimensions? The exploration of these questions has led to the development of sophisticated mathematical models, particularly those involving Calabi-Yau manifolds, which were discussed in Part 3. These manifolds, complex, multidimensional shapes, represent the possible ways in which the extra dimensions compactify, and the shape of these manifolds directly impacts the value of G. Different shapes lead to different vibrational modes, and consequently, different values for the fundamental constants. It's a remarkably intricate and subtle relationship. It's important to remember that string theory is still a work in progress. While it offers a compelling framework for understanding the universe, it's also incredibly complex and mathematically challenging. The precise value of G remains a subject of ongoing research, and physicists are constantly exploring new ways to refine their models and test their predictions. However, the concept of G as a fundamental calibrator, linking string vibrations to fundamental constants, represents a significant advance in our understanding of the universe's origins and the nature of reality itself. It suggests a universe where everything, from the smallest particle to the largest galaxy, is intimately connected through the vibrations of tiny, one-dimensional strings, all governed by the value of this fundamental parameter. The universe, as string theorists often describe it, isn't quite a smooth, flowing river. Instead, it's a vast, shimmering tapestry woven from incredibly tiny vibrating strings. These strings are so small, far smaller than anything we can currently detect, that they appear to be the fundamental building blocks of everything we see: matter, energy, and even space and time itself. But this beautiful picture, initially conceived with only closed strings, quickly revealed a profound problem. The mathematics simply didn't work. It produced far too many particles, far too many different kinds of particles, to account for the observed diversity of the cosmos. The initial models predicted a chaotic soup of particles, a veritable explosion of possibilities, and it was clear something was missing. The core issue stemmed from how these strings were initially treated. Closed strings in their simplest form were considered to be strings that loop back on themselves, forming a closed cycle. These cycles, vibrating at specific frequencies, corresponded to different mass energy values. The mathematics associated with closed strings, primarily the Polyakov-Witten theory, was successful at describing certain aspects of string theory, particularly the behavior of strings in a curved background. However, this framework couldn't fully explain the spectrum of particles observed in our universe. It essentially produced a large number of excited states of the string, each contributing to the particle count. Then came the crucial realization: these closed strings weren't the only kind. To solve the problem, string theorists introduced a second type of string: open strings. Open strings, unlike their closed counterparts, have free ends. They don't loop back on themselves. Instead, they terminate in what are called D-branes. D-branes are essentially surfaces or membranes within the string theory's landscape, and they play a hugely significant role. They are not merely passive backgrounds. They actively participate in the dynamics of the theory. The introduction of D-branes fundamentally altered the mathematical landscape. It allowed theorists to consume some of the excess particles predicted by the closed string models. Think of it like this: a closed string, vibrating in a particular way, was inherently unstable. It was constantly trying to transition into an open string state. The D-branes acted as a kind of trap, preventing this transition and effectively reducing the number of unstable modes. The mathematics of open strings, particularly the Green-Schwarz action, provided a much more accurate description of the particle spectrum. It successfully accounted for the observed masses and quantum numbers of fundamental particles like quarks and leptons. But the story didn't end there. The D-branes themselves possess their own dynamics and can also vibrate, contributing further to the theoretical particle content. These D-brane vibrations also generate gauge fields, the force carriers responsible for the fundamental forces of nature: electromagnetism, the weak force, and the strong force. The beauty of the open string approach lies in its ability to incorporate gravity naturally. General relativity, Einstein's theory of gravity, is already embedded within string theory. The graviton, the hypothetical particle that mediates gravitational force, is one of the vibrational modes of a closed string. However, the open string framework further strengthens this connection. The D-branes themselves are inherently space-time objects, and their interactions contribute to the curvature of space-time, thus explaining gravity on a fundamental level. Crucially, the different types of D-branes also introduce a new level of complexity. There aren't just one or two kinds of D-branes. There's a whole spectrum, each characterized by different numbers of open strings attached to it. These different D-brane types lead to a vast landscape of possible solutions to the string theory equations. A landscape with an estimated 1050 different valleys, each representing a different universe with potentially different physical laws. The exploration of this landscape is a major focus of contemporary string theory research. It's a challenging endeavor, seeking to understand how the different solutions relate to each other, and more importantly, how we might find a solution that describes our own universe. The theory doesn't offer a single, definitive answer, but rather a framework for exploring the possibilities. Furthermore, the concept of open strings has profound implications for our understanding of space and time. The D-branes, being objects within spacetime, suggest that spacetime itself might not be a fundamental, unchanging entity, but rather an emergent property arising from the interactions of these strings and D-branes. This idea challenges our most basic assumptions about the nature of reality. The ongoing research into open strings continues to refine the theory, providing increasingly precise predictions and offering tantalizing glimpses into the underlying structure of the cosmos. It's a journey of profound intellectual discovery, pushing the boundaries of our understanding of the universe and its fundamental constituents. It's a story still being written, one vibration at a time. The elegant equations of string theory, as we've explored, suggested a universe far richer and more complex than our everyday experience allows us to grasp. But the initial attempts to fully describe this universe, focused solely on vibrating strings, ran into a significant problem. They predicted an enormous number of particles, far more than we observed. It was as if the universe was screaming, "There's something missing." Physicists needed a clever trick, a way to reduce the predicted number of particles without sacrificing the fundamental idea of strings as the basic building blocks. That's where topological string theory began to blossom, offering a revolutionary approach rooted in the surprisingly relevant world of knot theory. At its core, topological string theory recognizes that a vibrating string isn't just a simple, one-dimensional object. Instead, it posits that a string can exist in 3 dimensions, a tiny, curled-up space. But this curled-up space isn't necessarily smooth and continuous like a familiar surface. It can be highly distorted, twisted, and knotted. These knots, mathematically represented by topological structures, become the key to understanding interactions between strings. The string itself doesn't simply vibrate in a single, simple way. It can exist in a multitude of different configurations, each corresponding to a different knot. Think of it like this. A simple string vibrating in a straight line represents one possible state. However, if you imagine that string passing through a tiny, tiny tunnel, a miniature wormhole, its vibration would be affected. The geometry of that tunnel, its twists and curves, would become part of the string's overall description. This isn't a physical tunnel in the sense we understand it, but a mathematical construct, a way of representing the complex interplay of the string with its surrounding space. Each distinct knot configuration, a figure 8, a trefoil knot, a linking of 2 knots, represents a different mode of vibration, and importantly, a different way for strings to interact. The crucial connection is made through the mathematics of knot theory, pioneered by mathematicians like Frederick Pollock and Lewis Carroll. Knot theory deals with the properties of knots, how they can be linked, untied, and interwoven. String theorists realized that the number of ways a string can be knotted, along with the specific geometry of those knots, directly corresponds to the number of possible interactions between strings. Each knot represents a unique quantum state, a distinct channel through which strings can exchange energy and momentum. This exchange isn't just a simple vibration. It's the fundamental process of particle creation and annihilation, the very essence of quantum mechanics. Furthermore, topological string theory allows for the possibility of branch strings. Imagine a string that, instead of simply passing through a single point in space, splits into two or more strings at that point. This branching introduces even more complexity, creating a network of interacting strings. These branched configurations, represented mathematically by branched covers of Riemann surfaces, become incredibly important in describing the interactions within a black hole, a topic that will later become central to understanding the very structure of space-time. The beauty of topological string theory lies in its elegance and its ability to resolve the overproduction problem. By considering the intricate topologies of strings, the knots and branched configurations, the theory naturally limits the number of possible interactions, and thus, the number of particles that can be created. The mathematics simply constrains the possibilities, leading to a much more manageable and ultimately more realistic picture of the universe. Initially, the calculations involved in topological string theory were incredibly difficult, relying on advanced techniques in complex analysis and topology. However, as computers became more powerful, researchers began to explore these calculations, uncovering surprising results. One significant discovery was the prediction of tadpole loops, configurations where a string splits into two and then immediately rejoins, creating a massless particle. These tadpole loops were later confirmed experimentally, providing strong support for the theory. The implications of topological string theory extend far beyond simply solving the overproduction problem. It provides a framework for understanding the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces as different modes of vibration of the strings. It suggests that gravity isn't just a force, but a manifestation of the string's interaction with the fabric of spacetime itself. Moreover, topological string theory is intimately linked to the concept of branes, higher dimensional objects in which strings can exist. These branes, often visualized as membranes, become critical in the development of M-theory, a unifying theory that encompasses all 5 consistent string theories. The journey into the depths of string theory continues, with each new discovery adding another layer of complexity and wonder to our understanding of the cosmos. The universe, as string theory proposes, isn't built of tiny billiard balls, but of incredibly minuscule vibrating strings. These strings, however, aren't just randomly vibrating. Their modes of vibration determine the properties of the particles we observe: electrons, quarks, photons, everything. For a long time, physicists wrestled with the stark contradiction presented by black holes. According to Einstein's general relativity, anything that falls into a black hole, matter, light, information, is utterly lost. The event horizon, that point of no return, obliterates everything from our view, and with it seemingly all knowledge of what crossed it. This presented a profound problem. Physics, at its core, demands that information is always conserved. It must be possible to trace the evolution of a system backward in time, and to understand how a state leads to another. But if information vanishes into a black hole, this fundamental law is broken. The situation grew more complicated with the rise of Hawking radiation. Stephen Hawking demonstrated that black holes aren't truly black. They emit a faint thermal radiation due to quantum effects near the event horizon. This radiation, initially thought to be purely random, posed another challenge. If black holes were simply radiating away energy in a thermal pattern, then the information about the material that fell in was permanently lost as well. It was like burning a book. The smoke and ashes contained no trace of the words that were once written. The fate of that information was sealed. Then, a radical idea began to germinate within the string theory community. What if the strings themselves played a role in the black hole's behavior? And more specifically, what if the event horizon itself was composed of strings? This concept, initially dubbed black strings, suggested that the familiar laws of space-time, as we understand them, don't hold true at the extreme conditions near a black hole. Instead, the event horizon would be a complex, vibrating landscape of these fundamental strings. These black strings aren't simply static barriers. They are actively interacting, constantly switching between different vibrational modes. Each mode represents a different type of particle, and the precise way these strings interact within the event horizon could, theoretically, encode the information about everything that has ever fallen in. It's like a cosmic record, with each vibration representing a piece of data. The initial idea proposed that the strings would absorb all the information, effectively becoming a black string memory. The crucial element is that the strings aren't just passively absorbing. They are re-emitting the information in a transformed form. This transformation isn't a simple erasure, but a complex process of encoding and re-encoding the information within the string's vibrational states. Think of it like a highly sophisticated encryption and decryption system operating at the most fundamental level of reality. The information isn't lost. It's simply hidden in a format we haven't yet fully understood. The specifics of how this transformation occurs are incredibly complex, deeply rooted in the mathematics of string theory and quantum gravity. It's likely that the strings would eventually decay back into fundamental particles, not in a singular, obvious way, but through a cascade of interactions and transformations within their vibrational landscape. The black string system would, in essence, be a giant quantum computer, constantly processing information and eventually releasing it as a new, albeit altered, form of radiation. One of the most intriguing aspects of this model is its potential to resolve the information paradox without requiring a wormhole solution. The idea that information might escape through a tunnel connecting the inside and outside of the black hole. The black string model suggests that information is retained entirely within the black hole's structure, and it's released gradually over an extraordinarily long period. It's not a sudden burst of information, but a slow, subtle leakage that perfectly complies with the laws of conservation. Furthermore, the black string approach offers a framework for understanding the no-hair theorem, which states that black holes are completely characterized by just three properties: mass, charge, and angular momentum. If the event horizon is made of vibrating strings, Each string possesses a unique set of vibrational properties. These properties combined completely define the black hole. It doesn't need to remember the specifics of what fell in. It simply embodies the information in its fundamental structure. The mathematical tools used to explore this model are immensely challenging, requiring advanced techniques from string theory, quantum field theory, and statistical mechanics. However, simulations and theoretical calculations have begun to suggest that the black string model could indeed provide a consistent framework for understanding black hole evaporation and the information paradox. It's a reminder that even the most perplexing mysteries of the universe may be solved by exploring the most fundamental building blocks of reality, the vibrating strings that underpin our existence. It's important to note that the black string model is still largely theoretical. Experimental verification remains a significant hurdle. However, it represents a potentially revolutionary shift in our understanding of black holes and the nature of information in the universe. It suggests that black holes aren't just cosmic garbage disposals, but dynamic information processing systems, deeply intertwined with the very fabric of reality. The continued exploration of black strings could ultimately unlock some of the deepest secrets of the cosmos. The elegant solution proposed by Gabriel Veneziano in 1968 and further developed by Joseph Pollack wasn't just about describing strings. It was about understanding them as fundamental components of a quantum field, much like electrons or photons. This evolved into what we now call string field theory. The core idea was to treat strings not as isolated, vibrating entities, but as excitations, like ripples, within a quantum field, analogous to how an electron is an excitation within the electromagnetic field. Instead of a single string existing in space, we imagined countless strings permeating all of space-time, constantly appearing and disappearing, interacting with each other, and forming the very fabric of reality at the smallest scales. This framework demanded a radical shift in perspective. Previously, string theory largely relied on a classical approach, describing the strings, properties, and interactions through equations derived from classical field theory. But to truly grapple with the quantum nature of strings, their wave-like behavior, and the uncertainty inherent in their properties, we needed to fundamentally integrate the string concept within a quantum field's mathematical structure. The field itself, let's call it the string field, would contain the degrees of freedom associated with all the strings present at any given point in space-time. The mathematical tools used to describe this string field were heavily influenced by quantum mechanics. The field equations, resembling those of the standard model of particle physics, dictated how strings interacted. Crucially, the exchange of energy and momentum between strings wasn't mediated by a single particle, like a photon. Instead, it was mediated by other strings, strings propagating through the string field itself. These exchanges were described by interactions that resembled what we know as scattering amplitudes in quantum mechanics. Essentially, an incoming string would interact with the string field, producing outgoing strings, and the strength of these interactions was determined by the specific interactions encoded within the string field's equations. These interactions weren't just about simple collisions. They allowed for the creation and annihilation of strings, effectively tunneling through energy barriers, a direct consequence of the quantum nature of the system. The string field wasn't a static background. It was constantly fluctuating, responding to the interactions happening between the strings. This dynamic behavior was described by operators acting on the string field, similar to how operators act on wave functions in quantum mechanics. These operators allowed us to calculate the probability of different string interactions occurring, leading to the scattering amplitudes we previously discussed. A key innovation was the introduction of tachyon fields. Tachyons, theoretical particles that always travel faster than light, emerged naturally within the string field framework. These fields were associated with strings that traveled at the maximum possible speed, the speed of light, within the string field. They played a crucial role in describing the interactions between strings and were intimately linked to the mathematics of scattering amplitudes. The propagation of these tachyon fields within the string field produced patterns of interference, much like the interference patterns observed when waves meet. These patterns dictated the probabilities of various scattering events, offering a deeper understanding of how strings interacted. The string field also provided a framework for incorporating gravity, which was a significant challenge in earlier string theory formulations. The graviton, the hypothetical particle that mediates gravitational force, naturally emerged as a massless excitation within the string field. This wasn't just a tacton addition. The equations of the string field themselves implicitly contained gravitational terms, reflecting the fact that strings, being fundamental objects, would experience gravity just like any other object. Furthermore, the dynamics of the string field itself could be influenced by gravity, leading to a self-consistent description of gravity within the framework of string theory. Mathematical techniques, primarily those developed in quantum field theory, including renormalization, a process used to handle infinities that arise in calculations, were employed to make sense of the string field. Renormalization allowed physicists to consistently extract meaningful physical predictions from the complex equations of the string field, even when they initially appeared to lead to infinite results. This was a testament to the power of quantum field theory to tame seemingly intractable calculations. The string field's greatest strength lay in its ability to generate a vast landscape of possible string configurations. The equations describing the string field didn't dictate a single, rigid solution. Instead, they allowed for an enormous number of different solutions, each corresponding to a different vibrational mode of the strings. This landscape is incredibly complex, with each region representing a distinct set of physical laws and constants. This complexity has led to discussions about the role of the string field in providing a mechanism for the anthropic principle, the idea that the fundamental constants of nature are fine-tuned for the existence of life. Perhaps our universe exists simply because it's one of the many possible solutions within this enormous string field landscape. While string field theory remained a predominantly theoretical construct for many years, it provided a crucial foundation for developing more refined string theory models, including the M-theory, and continues to inspire research aimed at understanding the deepest mysteries of the universe. It wasn't just about describing strings, but about building a coherent and consistent quantum theory of everything, one rooted in the fundamental interactions between strings within a dynamic, fluctuating quantum field. The realization that string theory, in its most complete forms, doesn't neatly predict a single universe, but rather an almost unimaginable multitude, arose gradually, like a slow-forming geological formation. Initially, string theorists were exploring different ways to solve the equations describing these vibrating strings. They discovered that the equations, when treated as a mathematical problem with no specific solution, dictated by observation, yielded an absolutely astonishing number of possibilities. Each different solution corresponded to a different set of fundamental constants: the strength of gravity, the mass of electrons, the constants governing the forces that hold everything together. It wasn't just a few slightly different universes. It was an unfathomable ocean of them, estimated to contain perhaps 10,500 different solutions. This wasn't a problem, not initially. It was a glorious, bewildering discovery. It meant that string theory, at its most fundamental, was incredibly rich and flexible. But this richness quickly presented a strange and unsettling question. If there are so many possibilities, why do we find ourselves in a universe with the specific properties it does? Why isn't the cosmological constant, which determines the expansion rate of the universe, a completely different value? Why is the mass of the proton exactly what it is? Why are the forces of nature arranged in the way they are? These questions demanded an explanation, and string theory, on its own, couldn't provide it. That's where the anthropic principle entered the picture. It's a complex idea, often misunderstood, and it comes in several forms. At its core, it essentially says that we observe the universe to be the way it is because if it were any different, we wouldn't be here to observe it. It's a selection effect, a kind of cosmic filtering. It's not a scientific explanation in the traditional sense. It doesn't tell us how the universe came to be, but rather it offers a framework for understanding why we observe a universe suitable for our existence. There are different versions of the anthropic principle. The weak version simply states that we should only consider universes that allow for observers to exist. The strong version proposes that the universe must have properties that allow for life to arise at some point in its history. The most commonly discussed variant is the fine-tuning argument, which focuses on the precise values of physical constants. These constants are incredibly sensitive. Even slight changes would render the universe sterile, unable to form stars, galaxies, or, ultimately, life. For example, if the gravitational constant were even slightly stronger, stars would burn out too quickly, and complex elements wouldn't have had time to form. If it were weaker, stars wouldn't ignite at all. The idea isn't that the universe was deliberately designed for us. That's a misconception. Instead, The string landscape offers a scenario where many universes exist, and by chance, our particular region of space happened to have the right conditions for the formation of matter and, eventually, life. Think of it like rolling a giant die with a huge number of sides, each representing a different universe. Most of these universes would be completely inhospitable, filled with unstable matter, extreme temperatures, or forces that prevent the formation of complex structures. But by pure luck, one of the rolls results in a universe like ours. The string landscape isn't a single monolithic structure. It's a vast, complex topology, often visualized as a seven-dimensional landscape with hills and valleys. Each valley represents a potential solution to the equations of string theory, corresponding to a different set of fundamental constants. Our universe resides in one of these valleys, a valley that happens to have the specific values of constants that allow for the existence of stable atoms, stars, and ultimately us. The shape of this landscape is determined by the compactification, the way extra-spatial dimensions, predicted by string theory, are curled up and hidden from our view. This landscape doesn't explain why the landscape has the shape it does, or why our particular valley exists. It simply describes the observed consequences. It's a statistical argument. It's essentially saying that if there are enough possibilities, then, inevitably, one will be suitable for life. The sheer number of solutions, 10,500, makes the existence of a life-permitting universe virtually guaranteed, even though it seems incredibly improbable from our limited perspective. However, the anthropic principle, and particularly the string landscape, isn't without its critics. Some argue that it's a way of avoiding fundamental questions about the origin and nature of the universe. It's a post hoc explanation, fitting the observed data to the theory rather than the theory arising from a deeper understanding of reality. Others suggest that it's simply a reflection of our own biases. We observe a life-permitting universe because we are here to observe it. Despite the criticisms, the string landscape remains a central concept in string theory, representing a profound and challenging perspective on our place in the cosmos. It highlights the incredible complexity and beauty of the theory, and forces us to confront the possibility that our universe is not a random accident, but rather a consequence of an unimaginably vast and intricate landscape of possibilities. The quest to understand the shape of this landscape and how it led to our existence continues to drive research in string theory, offering a tantalizing, if still largely mysterious, glimpse into the very fabric of reality. The prevailing models of the early universe, the Big Bang Theory, paint a picture of an incredibly hot, dense state rapidly expanding outwards. For decades, physicists wrestled with the immediate aftermath of this expansion, trying to understand what existed in those first fleeting fractions of a second. It was during this period, roughly between 10.3 and 10.32 seconds after the Big Bang, that string cosmology began to emerge as a serious contender. This isn't simply about adding strings to the existing Big Bang story. It's a fundamentally different perspective on the very genesis of space and time. The initial moments following the Big Bang are characterized by an immense energy density, far exceeding anything we experience today. In standard cosmology, This energy is described through the framework of quantum field theory, particles popping in and out of existence, governed by the equations of relativity. However, string theory provides a radically different and potentially more complete description of this extreme environment. The fundamental idea is that the universe wasn't born from a singularity, but from a state governed by strings. These aren't the guitar strings we know. They are one-dimensional, vibrating objects, incredibly tiny, far smaller than anything we can currently detect. Their behavior is dictated by the laws of string theory, which include extra-spatial dimensions beyond the three we directly perceive. The crucial component of string cosmology is its ability to address the problem of inflation. Inflation proposes a period of exponential expansion in the very early universe, driven by a mysterious energy field called the inflaton. This inflation smoothed out the universe, explained its homogeneity and isotropy, its uniform appearance in all directions. But the standard inflationary models have difficulty reconciling with observations, particularly the precise measurements of the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB shows tiny temperature fluctuations, and the pattern of these fluctuations depends critically on the dynamics of inflation. String theory offers a novel explanation for inflation, intimately linked to the behavior of these fundamental strings. Initially, the universe was filled with a soup of vibrating strings, constantly fluctuating. As the universe expanded, these strings began to interact, forming larger and larger objects, composite particles like quarks and leptons. Crucially, certain vibrational modes of these strings, particularly those corresponding to specific energy levels, exhibited behaviors remarkably similar to what we'd expect from a scalar field driving inflation. These specific vibrational modes, known as inflaton strings, acted like a self-regulating feedback system. As the universe expanded and the energy density decreased, the amplitude of these inflaton strings would grow, driving further expansion. This process, elegantly described by string cosmology, naturally addresses the issue of reheating, the transition from the rapid expansion of inflation to the later, slower expansion phase we observe today. Reheating in standard models often involves introducing ad hoc assumptions about the nature of the inflaton field, but string cosmology naturally incorporates this transition through the dynamics of the inflaton strings themselves. Furthermore, string cosmology suggests that the geometry of space itself might have originated from the collective vibrations of these strings. The string landscape, a vast collection of possible solutions to string theory, indicates that there are countless ways the fundamental constants of nature, like the gravitational constant or the charge of an electron, could have been set. If these strings were vibrating in specific ways, they could have imprinted a characteristic curvature on spacetime, ultimately leading to the observed properties of our universe. This isn't a simple replacement of the Big Bang with string cosmology. It's a deeper integration. The early universe isn't merely expanding. It's evolving through the intricate dance of vibrating strings. The expansion itself is a consequence of these vibrational modes, and the observed properties of the universe its geometry, its fundamental constants, are, in a sense, encoded within the dynamics of these strings. One of the most intriguing aspects of this model is its potential to explain the initial conditions of the universe. The string landscape offers a mechanism for generating a wide range of possible universes, each with its own set of fundamental constants. Our universe, with its seemingly fine-tuned values, might simply be one outcome within this vast ensemble. It's a reminder that the laws of physics, as we understand them, may not be universal, but rather a specific configuration arising from the chaotic dynamics of the early universe. Of course, string cosmology is still a theoretical framework, and there's no direct experimental evidence to confirm it. However, ongoing research in cosmology and particle physics continues to explore connections between the early universe and the principles of string theory. The search for gravitational waves, ripples in spacetime predicted by general relativity, could provide crucial evidence, perhaps even detecting the subtle signatures of string vibrations during the inflationary epoch. The future of cosmology might well depend on unlocking the secrets hidden within the quantum realm, where the fundamental building blocks of reality are nothing more than vibrating strings. String theory, at its heart, strives for a remarkably elegant description of the universe. It proposes that the fundamental building blocks aren't point-like particles as classical physics suggests, but rather incredibly tiny, vibrating strings. The different ways these strings vibrate correspond to different particles: an electron, a photon, a quark, each with its own unique energy and momentum. However, this initial formulation quickly revealed a problem. String theory, in its simplest forms, produced an enormous number of possible solutions, a landscape of universes, each with vastly different physical laws. This felt like an overwhelming complexity, a tangled mess of possibilities. Physicists began to explore ways to connect these seemingly disparate solutions, to reveal underlying relationships, and to simplify the landscape. This is where dualities emerged as a powerful tool. A duality essentially states that two different descriptions of a physical system are, in fact, equivalent. They are two sides of the same coin, representing the same underlying reality but viewed through different lenses. These dualities aren't just mathematical tricks. They hint at a deeper symmetry in the universe. One of the first and most significant dualities developed was T-duality, named after Edward Witten, who played a crucial role in its formulation. T-duality deals with the concept of distance in string theory, but not the distance we typically experience. Our familiar notion of distance is determined by the speed of light. It's how far something travels in a given amount of time. However, string theory suggests that there's another dimension, a compactified, curled-up dimension, which dictates the fundamental distance scale. Think of a garden hose. When you see the full length of the hose, it appears one-dimensional. But if you curl the hose into a circle, that same one-dimensional length now exists within a two-dimensional space, the surface of the hose. Similarly, in string theory, the extra dimension, the compactified dimension, is curled up so small that we don't directly perceive it. The size of this compactified dimension determines the fundamental length scale of the universe. Different radii for this curled-up dimension lead to different physical properties. A larger radius would result in a larger fundamental length, while a smaller radius would produce a smaller one. Importantly, T-duality states that any two string solutions that differ only in the radius of this compactified dimension are, in a precise sense, equivalent. It's like switching between different views of the same physical space, each defined by a different value for this fundamental scale. This allows physicists to make calculations and predictions even when starting with seemingly unrelated solutions. The math often simplifies beautifully once the duality is recognized. Another crucial duality is S-duality, and it's related to the concept of strength in the interactions between strings. While T-duality deals with length, S-duality focuses on the coupling constant, the strength of the forces governing the interactions between strings. Imagine a guitar string. The tension of the string directly affects how readily it vibrates and how much energy is needed to excite those vibrations. In string theory, the strength of the interactions between strings is determined by a parameter analogous to tension. S-duality proposes that any two string solutions that differ only in this coupling constant are also equivalent. This means that a string theory with a very strong coupling constant can be transformed into an equivalent theory with a very weak coupling constant, and vice versa. This is profoundly counterintuitive. A very powerful interaction can be rewritten as a very weak one, and vice versa. The connection between T-duality and S-duality is deep. It turns out that a particular transformation, a transformation matrix, can simultaneously change the radius of the compactified dimension and the coupling constant. This suggests that these two seemingly independent properties are, in fact, intimately linked. The specific relationship is described by a mathematical object called the Sycamore matrix, named after a particularly complex and beautiful mathematical construction. Understanding the Sycamore matrix has been a major focus of research in string theory, as it provides a way to navigate the vast landscape of possible solutions. These dualities aren't just theoretical exercises. They have real consequences for our understanding of the early universe. String cosmology, as explored previously, relies heavily on these dualities. The compactified dimensions, dictated by T-duality, played a role in the rapid expansion of the universe in the moments following the Big Bang. The specific geometry of these dimensions influenced the energy scales at play, and consequently, the rate of inflation. Moreover, the relationships described by the Sycamore matrix provide a framework for understanding how different string theories might have emerged during the inflationary epoch. Ultimately, the dualities in string theory represent a triumph of mathematical elegance. They demonstrate that the universe, at its most fundamental level, is far more symmetric and interconnected than we initially imagined. They provide powerful tools for navigating the complex landscape of possible solutions and offer tantalizing glimpses into the deepest mysteries of the cosmos. The ongoing research into these dualities continues to shape our understanding of string theory and its potential to unlock the secrets of the universe. The intricate dance of strings, vibrating in 10 dimensions, continues to reveal a fascinating and somewhat perplexing aspect of string theory: the bootstrap principle. It's a concept that speaks to the very foundations of how the universe, as we observe it, might have come to be, and it's intimately linked to the idea of self-consistent solutions. Before us lies a landscape of possibilities, a vast, incredibly complex string landscape, teeming with different configurations and interactions. This landscape isn't just a random collection of solutions. It's governed by a surprisingly elegant rule: that the properties of the universe, its fundamental constants, its dimensionality, even the very laws that dictate how particles interact, are, in a sense, baked in by the strings themselves. Consider this. Our universe appears remarkably stable. The fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, operate with precise values, allowing for the formation of atoms, stars, and galaxies. If these forces were even slightly stronger or weaker, matter as we know it couldn't exist. Stars wouldn't burn, atoms wouldn't hold together, and the universe would be a radically different, far less hospitable place. The bootstrap principle suggests that this inherent stability isn't due to a grand, external designer or a fundamental law imposed from above. Instead, it arises from the way strings interact with each other. The core idea is that each interaction between strings contributes to the overall energy and, crucially, to the values of the forces we observe. Let's delve into an example. Imagine two strings vibrating in a particular way. Their interaction doesn't simply exchange energy, it creates a residual effect. This effect subtly alters the properties of the surrounding space, effectively changing the strength of the gravitational force in that region, or perhaps influencing the charge of a particle passing through. Now, consider a whole collection of strings interacting. Each interaction adds to this residual effect, building up a complex web of influences. The key is that this process doesn't necessarily produce a net change. Instead, the system settles into a state where the residual effects precisely cancel each other out, leaving the observed values of the forces unchanged. It's like a delicate balancing act, a constant adjustment driven by the inherent properties of the strings themselves. This cancellation isn't a passive process. It's an active one, driven by the quantum mechanical nature of the strings. The interaction between strings is governed by probability. The system will tend to settle into configurations where the probability of interaction is maximized, leading to the most stable, self-consistent solution. Let's step back and consider the implications of this. If the universe's properties are determined by these self-consistent string interactions, it implies that the landscape of string solutions isn't simply a collection of lucky configurations. Rather, it's the result of a process of selection, a refinement guided by the fundamental dynamics of the strings. The most stable configurations, those that naturally lead to self-consistent solutions, are the ones that win out, and these are the ones that we observe. It's often described as a kind of recursive definition. The properties of the universe are defined by the interactions of strings. These interactions, in turn, determine the properties of the universe, which then further influence the interactions. It's a closed loop, a self-sustaining system. Furthermore, the bootstrap principle offers a potential explanation for why our universe seems so finely tuned for life. It doesn't require a divine hand, but rather a remarkably effective selection mechanism inherent within the strings themselves. The vast majority of string landscape solutions would be unstable, leading to a universe devoid of the conditions necessary for complexity. Only a small fraction, those that naturally lead to self-consistent solutions, are viable. We, and the universe as we know it, exist within that small, privileged subset. The beauty of this approach lies in its elegance. It provides a framework for understanding why the universe has the properties it does, without invoking external forces or a predetermined plan. It's a bottom-up explanation, driven by the intrinsic characteristics of the fundamental building blocks of reality. It's important to acknowledge that the bootstrap principle isn't without its challenges. The string landscape is incredibly vast, perhaps even infinite, making it extraordinarily difficult to precisely calculate the probabilities of different solutions. Moreover, the mathematical tools needed to fully explore this concept are still under development. However, it represents a powerful and increasingly compelling idea, offering a potential pathway toward a deeper understanding of the universe's origins and its remarkable stability. As we continue to probe the intricate details of string theory, the bootstrap principle serves as a reminder that the answers to some of the biggest questions about our existence might be found not in grand, overarching theories, but in the subtle, self-consistent interactions of the smallest components of reality, the vibrating strings that form the very fabric of space and time. The tantalizing theoretical framework of string theory, with its vibrant landscape of possibilities, has prompted physicists to consider how to actually find evidence for its existence. It's not enough to simply say a particular model is elegant or mathematically consistent. The ultimate test, as with any scientific theory, lies in observing the universe and seeing if it behaves in ways that align with string theory's predictions. This leads to the crucial area of string scattering experiments, designed to probe the fundamental structure of reality at incredibly small scales far smaller than anything we've ever been able to directly observe. The core idea behind these experiments centers on the notion that strings, being incredibly tiny, are likely to interact with each other. These interactions, even if incredibly rare, could manifest as detectable events. The Large Hadron Collider, LHC at CERN, is the primary venue for conducting these searches, although researchers are also looking for evidence at future, higher-energy colliders. The fundamental strategy involves smashing together beams of protons at near-light speed. When these protons collide, the energy released can, theoretically, momentarily create a black hole, not the kind that swallows stars, but a microscopic one, incredibly short-lived, predicted by Einstein's theory of general relativity. However, string theory posits that these black holes wouldn't be the final stage. Instead, they'd be unstable, rapidly decaying. The key prediction is that during this decay, instead of simply emitting Hawking radiation, the theoretical process by which black holes slowly evaporate, The black hole would also produce a shower of new, highly excited particles, particles that are predicted by string theory. These aren't your everyday particles like electrons or quarks. They're the vibrational modes of the fundamental strings themselves. The most intensively studied signature for these string scattering events revolves around the production of superluminal particles, particles that travel faster than the speed of light. Now, this might seem like a violation of Einstein's theory of relativity, but it's a crucial element in some string theory models. The decay products aren't traveling through space faster than light. Rather, the appearance of these superluminal particles is a consequence of the way spacetime itself is warped and distorted during the black hole's rapid collapse. It's a fascinating interplay between gravity and quantum mechanics. The LHC has been painstakingly searching for evidence of these superluminal particles, specifically looking for a distinct bump in the energy spectrum of the particles produced in proton collisions. This bump would represent the sudden appearance of these strings' vibrational modes. The detectors at the LHC, like ATLAS and CMS, are designed to precisely measure the energies and momenta of these particles, attempting to identify this subtle signal. So far, the results have been inconclusive. The experiments have observed a slight excess of particles at very high energies, but it's difficult to rule out this excess due to the sheer complexity of the collisions and the inherent statistical fluctuations. It's akin to trying to isolate a single, tiny drumbeat within a massive, chaotic orchestra. Beyond the LHC, physicists are also considering experiments at future colliders that would offer higher energies and, consequently, the ability to probe smaller scales. The International Linear Collider, ILC, currently under development, is designed to collide electron beams, which provides a more controlled environment and allows for greater precision in measuring the properties of the produced particles. Similarly, proposals for a future circular collider, FCC, at CERN would involve a much larger, more powerful accelerator. Another intriguing approach involves searching for subtle distortions in spacetime itself. Some string theory models predict that the black hole decay process could create tiny, fleeting ripples in spacetime, known as gravitational waves. These gravitational waves, if produced and detected, would provide direct evidence of the spacetime distortions associated with the black hole's collapse, a key prediction of string theory. Scientists are actively developing highly sensitive detectors, such as LIGO and Virgo, to look for these incredibly weak gravitational signals. Furthermore, researchers are exploring the possibility of searching for fuzzballs, another theoretical object predicted by some string theory models. Fuzzballs are compact, stringy objects that could potentially replace the role of black holes, completely altering the dynamics of black hole decay and the production of gravitational waves. Detecting these fuzzballs would require extremely precise measurements of particle properties and interactions, pushing the limits of current experimental capabilities. The challenges are immense. The predicted signals are expected to be incredibly faint and short-lived, buried within a background of other particle interactions. The statistical uncertainties are enormous. However, The potential reward direct evidence for string theory and a revolution in our understanding of the universe is enormous. Each experiment, each measurement, brings physicists closer to unraveling the deepest mysteries of reality, potentially revealing the true nature of strings and the fundamental building blocks of existence. The search continues, a testament to human curiosity and our relentless pursuit of knowledge. The universe, as we understand it, is a place of incredible contrasts. On the largest scales, it's governed by the elegant, predictable laws of general relativity, penned by Albert Einstein. These laws describe gravity not as a force, but as a curvature of space-time, the very fabric of existence caused by mass and energy. A massive star, for example, warps the space around it, and that curvature is what we experience as its gravitational pull. It's a beautiful, profoundly powerful theory that explains everything from the orbits of planets to the expansion of the universe itself. But there's a fundamental problem. General relativity works best when dealing with large objects and slow movements. It struggles, desperately struggles, when we try to apply it to the incredibly small, the realm of quantum mechanics. Quantum mechanics, developed largely by Niels Bohr and Werner Heisenberg, governs the behavior of particles like electrons and quarks. In this world, things aren't smooth and predictable. Instead, energy and momentum exist in discrete packets called quanta. Particles can exist in multiple states simultaneously, a concept famously described as superposition. Furthermore, their position and momentum cannot be known with perfect accuracy. The more precisely we know one, the less we know about the other, a core principle embodied in Heisenberg's uncertainty principle. The issue arises when we attempt to describe gravity using the standard techniques of quantum mechanics. When physicists try to quantize gravity, to break it down into its smallest components like other forces, the math goes terribly wrong. Calculations yield infinite results, nonsensical predictions that contradict experimental observations. It's like trying to build a bridge with materials that instantly disintegrate when you apply any amount of pressure. The fundamental incompatibility between general relativity and quantum mechanics creates a crisis in our understanding of the universe. We need a new framework, one that can seamlessly merge these two pillars of modern physics. String theory enters the picture as a potential resolution to this profound puzzle. The core idea is startling. Instead of thinking of fundamental particles like electrons and quarks as point-like objects, string theory proposes that the most basic constituents of the universe are tiny, vibrating strings. These strings are unbelievably small, far smaller than anything we can currently probe with our most powerful instruments. Each different vibration mode of a string corresponds to a different particle: an electron, a quark, a photon, and yes, even the graviton, the hypothetical particle that mediates gravity. This seemingly simple shift has enormous consequences. The problem of infinities in quantum gravity vanishes. The very structure of the strings inherently prevents the formation of these problematic singularities. When physicists attempt to calculate interactions involving gravitons, for instance, the mathematics work smoothly, producing finite and physically meaningful results. The strings act as a natural regulator, smoothing out the calculations. String theory also introduces concepts like extraspatial dimensions. The mathematics of the theory only works if there are more than the three spatial dimensions we readily perceive. These extra dimensions are thought to be curled up, compacted at incredibly small scales, making them undetectable by current experiments. Imagine a garden hose lying flat. It appears one-dimensional. But if you start to twist it, a second dimension appears, curled up along the length of the hose. String theory suggests that the universe is similarly curled up, with these extra dimensions tucked away, influencing the fundamental forces and particle interactions. The beauty of string theory lies not just in its mathematical elegance, but also in its inherent ability to unify gravity with the other forces of nature. It's a framework that offers a potential solution to the long-standing problem of quantum gravity. However, it's crucial to acknowledge that string theory is still very much a work in progress. While the mathematics is compelling and the theoretical framework promising, direct experimental evidence remains elusive. Scientists are exploring various ways to test string theory indirectly. One approach involves searching for subtle deviations from general relativity's predictions at extremely high energies, energies that might be accessible at the Large Hadron Collider, LHC, and future particle accelerators. Physicists are also looking for evidence of extra dimensions, perhaps through observations of gravitational effects on light or other particles. Furthermore, research continues into the landscape of possible string theory solutions. The vast number of different ways the extra dimensions can be curled up, each potentially leading to a different set of physical laws. Understanding this string landscape is a major challenge, and it's believed that the conditions in our universe, the specific way the dimensions are curled up, represents a very small fraction of the total possibilities. Ultimately, string theory represents a bold and imaginative attempt to reconcile our understanding of the cosmos. It's a testament to the power of theoretical physics, a framework that challenges our fundamental assumptions about space, time, and the nature of reality itself. The search for a complete and experimentally verified theory of quantum gravity continues, driven by the desire to understand the very origins of the universe and the fundamental forces that shape it. The elegance of string theory, with its vibrating strings and extra dimensions, had captivated physicists, but a crucial question remained. How could we actually test this extraordinary idea? It wasn't enough to simply demonstrate that the mathematics worked beautifully. To truly understand string theory, scientists needed to find ways to connect it to the world we observe, to see if it predicted anything we could actually measure. This is where string phenomenology began to blossom, a field dedicated to exploring the potential observable consequences of string theory. Initially, the challenge seemed almost insurmountable. The fundamental scales of string theory, the size of the extra dimensions, for instance, were vastly smaller than anything we could probe with current technology. The typical estimates place these dimensions on the order of the Planck length, a distance roughly 10 sub-35/sub meters, far smaller than even the most powerful particle accelerators could reach. However, string theorists didn't abandon the quest. Instead, they began to explore scenarios where the effects of these tiny dimensions might become apparent through subtle shifts in the properties of particles we do know. One key area of investigation centered on the concept of supersymmetry. Supersymmetry proposes a symmetry between bosons, force-carrying particles like photons and fermions, matter particles like electrons. String theory naturally incorporates supersymmetry, and the precise way this symmetry is broken, the specific values it takes, plays a critical role in determining the masses of particles. The standard model of particle physics, which describes all known fundamental particles and their interactions, has a particular problem. It predicts that the Higgs boson should have a mass around 125 GeV, but experiments have found it to be closer to 126 GeV. Supersymmetry provides a natural mechanism to fine-tune the Higgs mass to this precise value. More specifically, string theory allows for a range of supersymmetric models, and each model predicts slightly different masses for the particles. By analyzing these predictions, physicists could potentially find hints of supersymmetry in the data coming from experiments like the Large Hadron Collider. The LHC searches for partners to the known particles, heavier versions of things like quarks and leptons. That would be a consequence of supersymmetry. These searches aren't looking for direct evidence of extra dimensions either, but rather for the altered masses and decay patterns that supersymmetry would introduce. Another intriguing avenue explored within string phenomenology is the possibility of brane worlds. The standard model, as we currently understand it, is embedded on a three-dimensional brane, a membrane-like surface within a higher dimensional space. This space has more than 3 dimensions, although most of them are curled up or compactified at incredibly small scales. Interactions between particles could then occur not just within our 3-dimensional space, but also through warping or bending of these extra dimensions. These extra dimensions aren't necessarily compact in a simple, ring-like shape. They could have incredibly complex geometries, and these geometries could subtly influence the properties of particles moving within our brane. For example, the strength of the gravitational force might be affected by the shape of the extra dimensions, leading to small but measurable deviations from Newton's law of gravity at very short distances. Experiments searching for these deviations are a relatively new area of research, and the sensitivity required is immense. Scientists are looking for changes in the gravitational force smaller than 1 part in a billion. Furthermore, string theory suggests the existence of Kaluza-Klein modes. These are essentially copy particles that arise from the compactification of extra dimensions. Each extra dimension corresponds to a new mode, and these modes have different masses. Just as a guitar string vibrates at different frequencies to produce different notes, these Kaluza-Klein modes vibrate at different energies, corresponding to different mass values. Detecting these modes would provide direct evidence of the existence of extra dimensions. String phenomenology also considers the possibility of sterile neutrinos. The standard model predicts the existence of 3 types of neutrinos, but experiments have revealed that they are much lighter than originally anticipated. String theory offers a natural explanation for this neutrino mass problem through the introduction of additional sterile neutrinos, which could exist in the extra dimensions. The calculations involved in string phenomenology are extraordinarily complex, requiring sophisticated mathematical techniques and powerful computer simulations. However, as theoretical understanding advances, so too does the ability to make precise predictions. Scientists are constantly refining their models, exploring different scenarios, and comparing their predictions with experimental data. The hope is that, eventually, a particular string theory model will emerge as the best fit to the data, providing concrete evidence for the existence of extra dimensions, supersymmetry, or other phenomena predicted by string theory. It's important to remember that string phenomenology isn't about proving string theory is right. It's about building a framework, a set of predictions that can be tested against observations. Even if no direct evidence is found, the continued exploration of string phenomenology is deepening our understanding of the fundamental laws of the universe and pushing the boundaries of what we thought was possible. The search continues, driven by the elegance and potential of string theory. The universe, as we generally understand it, relies on a beautiful, elegant framework built by Albert Einstein, general relativity. This framework describes gravity not as a force, but as the curvature of spacetime itself. Massive objects like planets and stars warp this fabric, and other objects follow the curves, giving the impression of being pulled together. It's a remarkably accurate description of the cosmos on large scales, galaxies swirling, black holes devouring light, the expansion of the universe itself. However, at the tiniest scales imaginable, the world gets incredibly strange. At the Planck scale, a length of roughly 1.6 x 10^35 meters, general relativity begins to break down, and the principles of quantum mechanics, which govern the behavior of particles at these scales, demand their attention. The problem isn't simply that our current theories clash. It's that they operate under fundamentally different assumptions about the nature of space and time. Quantum mechanics tells us that position and momentum aren't fixed properties of a particle, but rather exist within a probabilistic cloud. A particle doesn't have a definite location until it's measured. Instead, there's a range of possibilities, each with a certain probability of being observed. General relativity, in contrast, treats space and time as a smooth, continuous, and unchanging backdrop against which all physical events unfold. It's a static stage. This fundamental difference leads to mathematical inconsistencies when we try to combine the two. Attempts to quantize gravity, to describe gravity itself in terms of quantum mechanics, result in equations that produce nonsensical answers, like infinite energy densities. The standard approaches simply don't work, but a group of physicists, particularly those working with string theory, began to explore an entirely different way to think about spacetime. They began to consider a radical concept, that spacetime itself might not be smooth and continuous, but instead granular, discrete, and potentially non-commutative. The idea of non-commutative geometry, pioneered by mathematicians like Elaine Connes, offers a way to describe spaces where the order in which you perform measurements matters. Imagine a simple grid. If you measure the x-coordinate and then the y-coordinate, the result you get might be different if you had measured the y-coordinate first. The order of your measurements affects the outcome. This isn't just a mathematical curiosity. It's a reflection of the fundamental uncertainty in quantum mechanics. Applying this concept to space-time suggests that at the Planck scale, space and time aren't independent, smoothly varying entities. Instead, they're woven together into a complex interwoven fabric where the mathematical operations, specifically multiplication, don't behave in the way we're accustomed to. XY might not necessarily equal YX. The very act of measuring one dimension could subtly alter the other, creating a profoundly different geometry than the one we perceive at larger scales. This isn't about visualizing tiny squares or cubes. It's about changing the fundamental rules of mathematical calculation. It's as if the coordinates of space itself are entangled in a way that prevents us from simply applying our everyday geometric intuition. The implications are astonishing. It suggests that space-time isn't a passive backdrop, but an active participant in the universe's evolution, responding to measurements and interactions in a way that defies classical physics. Within the framework of string theory, this non-commutative geometry plays a crucial role in modeling the extra dimensions that string theorists propose. Rather than the single three spatial dimensions and one time dimension we experience, string theory suggests there might be 6 or 7 additional, curled-up dimensions, existing at the Planck scale. These dimensions aren't necessarily curled into tiny circles. Their geometry could be profoundly non-commutative. The interactions between strings vibrating in these complex, potentially non-commutative spaces would determine the properties of the particles we observe in our familiar 3 dimensions. The mathematics required to describe these non-commutative spaces is extraordinarily complex, far beyond the standard tools of general relativity. It involves advanced concepts from topology, category theory, and functional analysis. But the potential rewards, a deeper understanding of gravity, quantum mechanics, and the very nature of reality, are immense. Scientists are developing sophisticated computational techniques to simulate these spaces, hoping to uncover patterns and relationships that might reveal new insights into the universe's origins and its ultimate fate. Furthermore, non-commutative geometry offers a potential resolution to the cosmological constant problem, the enormous discrepancy between the theoretically predicted and the actually observed energy density of the vacuum. Some researchers believe that the non-commutative structure of spacetime at the Planck scale could automatically generate a non-zero vacuum energy, eliminating the need for a mysterious, unexplained cosmological constant. The journey to understand the universe at the Planck scale is undoubtedly challenging. It demands a radical shift in our thinking about space and time. But within the framework of string theory and non-commutative geometry, there lies the possibility of a profoundly different, and perhaps far more beautiful, understanding of the cosmos. It's a reminder that the most fundamental questions about our universe often lie hidden within the most complex and counterintuitive mathematical landscapes. The universe, at its most fundamental level, isn't made of tiny, point-like particles zipping around. Instead, a revolutionary idea, string theory, proposes that the very building blocks of reality are minuscule, vibrating strings. These aren't strings like those you might tie, but incredibly small, one-dimensional objects, far too small to ever be directly observed. Each string can vibrate in countless ways, much like a guitar string can produce different notes depending on how it's plucked. Each distinct vibrational mode corresponds to a different particle, an electron, a quark, or even a force carrier like a photon. Now, if you have a single string vibrating, it's a simple picture. But the real magic begins when you consider that these strings aren't isolated. They interact, they entangle, they form complex networks. These networks aren't just collections of strings. They begin to exhibit properties that aren't immediately apparent from looking at the individual strings. As these networks grow in complexity, something remarkable happens. They start to resemble what we experience as space and time. The key to understanding this transformation lies in the concept of compactification. Imagine a very long, coiled rope. From a distance, it appears as a single line. But as you get closer, you see that it's actually made of many tiny loops packed tightly together. Similarly, the higher vibrational modes of these string networks, the ones that don't correspond to observable particles, are thought to be curled up into incredibly small, compact dimensions. These dimensions aren't empty space. They're active, contributing to the overall dynamics of the network. These curled-up dimensions aren't just geometrical decorations. They fundamentally shape the behavior of the strings within the network. The size and shape of these curled dimensions determine the strength and nature of the interactions between the strings. This is where the concept of Calabi-Yau manifolds enters the picture. These are complex, multi-dimensional shapes, often involving 6 or 7 extra-spatial dimensions, that are considered the most likely ways these curled dimensions can be arranged. Different arrangements of these manifolds lead to different physical laws and properties. Consider a vast, interwoven tapestry. The individual threads of the tapestry represent the strings, and the patterns they form represent the complex string networks. If the tapestry is folded in a particular way, it creates a specific surface, a three-dimensional object with unique properties. Similarly, the arrangement of these Calabi-Yau manifolds dictates the geometry of the space within the string network. The remarkable aspect is that as these networks grow larger and more complex, the overall geometry of the space they occupy becomes increasingly smooth and predictable. The chaotic, fluctuating behavior of the individual strings begins to average out, leading to the emergence of what we perceive as classical geometry, the familiar three-dimensional space and time that governs our everyday experiences. It's as though the sheer number of strings and their intricate interactions create a stabilizing force, smoothing out the underlying quantum fluctuations. Think of a turbulent river. The individual water molecules are constantly colliding and moving in random directions. However, as the river flows further downstream, the water molecules become more organized, forming larger, more defined currents. Similarly, the quantum fluctuations within the string network are washed out by the collective behavior of the strings, leading to the emergence of classical geometry. Furthermore, the way these networks interact introduces new forces and interactions beyond the standard four: gravity, electromagnetism, and the strong and weak nuclear forces. These extra forces, mediated by the vibrations of the strings themselves, shape the curvature of space-time and influence the behavior of the strings. The dynamics of the string network essentially generates gravity, rather than simply allowing it to exist as a separate force. The beauty of this idea is that it offers a potential solution to some of the most perplexing problems in physics. It provides a framework for understanding how the universe transitioned from a highly fluctuating quantum state to the relatively stable classical state we observe today. It suggests that space-time itself isn't a pre-existing stage, but rather an emergent property arising from the complex dynamics of these fundamental string networks. While string theory remains largely theoretical, directly observing these strings is currently beyond our technological capabilities. It provides a compelling and elegant framework for understanding the universe at its deepest level. The exploration of string networks and their ability to generate space and time continues to drive research and push the boundaries of our understanding of reality. It's a story of how order can emerge from chaos, of how complexity can give rise to apparent simplicity, and of how a fundamental shift in perspective can unlock the secrets of the cosmos. The universe, as we've begun to understand, isn't quite as solid and straightforward as a neatly drawn picture. String theory, with its vibrating strings and extra dimensions, revealed a profound strangeness, a hint that our everyday perception of space and time might be a highly simplified illusion. For decades, physicists wrestled with the mathematical complexities, searching for a way to connect this elegant theory to the observable world. Then, a remarkable shift occurred, largely driven by the exploration of holographic principles and the astonishing AD-SCFT correspondence. These ideas, initially seen as purely theoretical, are now considered pivotal in shaping our understanding of gravity and the fundamental nature of reality. At the heart of the holographic principle lies a startling suggestion. The information content of a volume of space isn't stored within that space itself, but rather on its boundary. It's like a hologram, a 2D surface that, when illuminated correctly, creates a 3D image. The holographic principle proposes that our 3D universe might be a holographic projection of information residing on a distant 2D surface. This isn't about replicating the universe perfectly, but about encoding its properties, its geometry, its matter, and its energy onto this boundary. This idea emerged from research on black holes. Physicists began to notice a surprising relationship between the area of a black hole's event horizon, the point of no return, and the entropy, a measure of disorder or information, contained within the black hole. The connection was profound. Entropy, as we know, is related to the number of possible microscopic arrangements that can give rise to a particular macroscopic state. Black holes, despite their immense gravity, seem to obey a rule where their entropy was proportional to their surface area, not their volume. This suggested that all the information about what fell into the black hole, every particle, every interaction, was somehow encoded on the black hole's surface. This led to the radical conclusion that the universe, at its most fundamental level, might be described by information residing on a distant boundary, similar to the holographic projection. Simultaneously, a related concept, the AD-SCFT correspondence, began to solidify. This correspondence, proposed independently by Juan Maldacena and Gers Vernick, offers a particularly concrete and powerful illustration of the holographic principle. AD-S stands for anti-de Sitter space, a hypothetical spacetime that's negatively curved, like a saddle. Think of it as a space with a constant, gentle curve pulling everything inwards. CFT, or conformal field theory, is a specific type of quantum field theory that lives on the boundary of this AD-S space. The AD-SCFT correspondence essentially says that an exact mathematical duality exists between a theory of gravity, described by Einstein's equations in AD-S space, and a quantum field theory without gravity living on that same space's boundary. It's like having two entirely different descriptions of the same physical system, perfectly mirroring each other. A gravitational process in the curved AD-S space is intrinsically linked to a corresponding quantum field theory process on the boundary, and vice versa. The remarkable aspect is that the two descriptions are, in a sense, equally valid. Crucially, the strong interactions, the forces that govern the behavior of fundamental particles, which are notoriously difficult to incorporate into gravity theories, can be elegantly described by the CFT living on the boundary. This offers a potential pathway to solving some of the biggest challenges in theoretical physics. For example, scientists are using the AD-SCFT correspondence to study quantum gravity, the elusive theory that combines general relativity and quantum mechanics. The correspondence isn't just a mathematical curiosity. It's a powerful computational tool. Because the CFT on the boundary is often simpler to work with than the full theory of gravity in AD-S space, physicists can use the CFT to solve problems in the gravitational theory. Then, the solution is translated back to the AD-S space, providing insights into the gravitational system. Furthermore, this allows for the simulation of black hole physics, something previously considered impossible due to the extreme gravitational conditions. Scientists are actively exploring the implications of AD-SCFT for understanding phenomena like the early universe, where gravity and quantum effects were both incredibly strong. The correspondence suggests that the universe didn't begin with a singular point of infinite density, as initially proposed, but rather emerged from a more complex, fluctuating state described by the CFT. While the AD-SCFT correspondence is still being refined and explored, it represents a profound shift in our understanding of the universe. It's providing a framework for thinking about gravity not as a force, but as an emergent property, arising from the underlying quantum dynamics of the boundary. The holographic principle and AD-SCFT offer a tantalizing glimpse into a universe where reality is fundamentally encoded on a distant surface. A universe far stranger and more beautiful than we could have initially imagined. The quest to fully understand these concepts continues, promising further revolutionary discoveries about the nature of space, time, and everything in between. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The universe, with its strings and dimensions, now gently recedes from your awareness. Let your thoughts drift, calm and unhurried, like wisps of cloud across a twilight sky. Allow yourself to settle, to release, to simply be.